Alright, ladies and gentlemen, welcome to your second class recording. Again, just wanted to do this here when we're covering information to try and make it a little bit more efficient so we can use our time together in class to work on applications and examples, and I can just give you the information over recording when we're not necessarily together. Keep in mind though that this really does require that you guys watch these videos so that when you get to class you're ready to discuss the information, you're ready to apply the information, or ask questions if necessary. So the second part of our introduction to mechanics deals with graphing motion. I know that we've talked about in class that, and you've probably hopefully talked about before, we make graphs to look for patterns, to be better able to visually represent some measured data and look for the patterns and look for the comparisons between some measured data. For example, here we have a picture of two ladies swimming, and to the left we have a graph of the distance that those ladies traveled and the time it took them to travel that distance. So we'll assume that swimmer 1 is in the white cap and swimmer 2 is in the yellow cap, just based on our vantage point. Looking at this graph of the two swimmers and how far they went and how long it took them to go that far, we could probably make a couple of assumptions, or we could come to some conclusions about the motion of those two swimmers. First, we probably could see that both swimmers started at the same point at the same time, because their initial time and their initial distances are both in exactly the same spot. But in the first 10 seconds, swimmer 1 covers 20 meters worth of distance, whereas swimmer 2 only looks like she maybe covers about 10 meters worth of distance. I'm estimating, but that's probably a good bet, right? And that trend continues on and on and on. And if we look at 20 seconds, let's use a different color there. So after 10 seconds, swimmer 1 has opened up a lead over swimmer number 2. At 20 seconds, that lead has increased if we look at the distance between their two lines on the graph. And that lead continues to increase as time goes on and on and on. So in looking at measurements of motion on graphs allows us to imply some things about individual motions, but also make some comparisons a little bit easier. So we're going to start off with the simplest type of graph, and that's a position time graph. And as you may have guessed, right, a position versus time graph shows you the location of an object over a specified period of time. When we make position versus time graphs, time is always going to go on our x-axis. Position or distance, depending on what book you read, they'll label it differently, but more importantly, it's where something is. That position is going to go on the y-axis. And that's great, so we can tell where something is at a specified time. But as is often the case when we make these graphs, we're not just looking at the relationship between the two measured values. A lot of times we can imply or we can infer some information if we look at how those two variables are related. And in this case, we're going to look at the slope of this graph. So hopefully you remember from back in math class, way back in pre-algebra or whenever it was that you took it, that we define the slope of a line as rise over run. But then you get a little bit more sophisticated in your definition of the slope, and more generally speaking, we define the slope of any line or any graph as the change on the y-axis over the change on the x-axis. And we'll keep that definition here, but we'll apply it specifically to our graph. On our graph, the y-axis is distance, and it's being measured in meters. The x-axis is time, or is showing us the time, and it's measured in seconds. So if we have a meters value and a seconds value, I'm hoping that you remember from the past couple of days, if we have meters over seconds, that is our unit for velocity. So, right, here's meters over seconds, right? But remember that when IB does things, they try and make it in that straight line. So we take the seconds from the denominator of the fraction and we turn it into a negative exponent. Same thing, different notation. But that means that on a position versus time graph, the slope of that position versus time graph tells us the velocity of that object. We're going to start with simple motions, and what that does for us at this point is we're going to start with motions that are constant velocity motions. So let's look at a couple of examples and how the slope of this graph will tell us the velocity. So first, this graph over here on the left-hand side, right, there are three distinct sections. We have this section here at the beginning, we have this section here through the middle, and then we have this section here at the end. If we go back and apply the idea that the slope of a position versus time graph tells us velocity, we can see here with these three distinct sections of the graph, two of the slopes are actually the same. The yellow section and the blue section both have a zero slope. They're both horizontal lines. And in terms of the motion of the object, horizontal lines represent an object that is not moving. And like we said, like I just said, in this graph, we actually have two horizontal lines. So there are two sections of this specified time period where this object isn't moving. Now, they're at rest in both occasions, but they're in different spots because the y values of the graph during that section are different. This is much closer to the starting point than this one is. And that means that during the pink section, some type of movement had to have happened. Like I said, we're going to start off with the simplest case scenario with constant velocities. During this pink section right here, we see a straight line. Straight lines have constant velocity, straight lines have constant slope, regardless of where the straight line occurs on a graph. In this specific graph, a distance versus time graph, straight lines, constant slope, that's going to be sections where objects are moving with constant velocity. All right? So there's our first two examples of applying the idea that the slope of a graph can tell us something about the motion. So let's take a look at another picture. Again, we have three distinct sections here. We have this section here at the beginning that I've labeled yellow. This section, let's do something else. I'm going to go pink here. I'm going to go yellow here. And then I'm going to go, let's go purple for this section right through here. Okay? All right. First, yellow section. Horizontal line, zero slope. And again, that means that this object was at rest. But here, we have two distinct sections where there are constant non-zero slopes. And that means that there are two sections over this time interval that this object was moving. In both cases, because the slope is constant, that means that the object was moving with a constant velocity. But the difference in slope also describes what was going on. The first movement, the shallow slope section, right? A smaller slope means a slower speed or a slower velocity. It wasn't going very fast at the beginning. Remember the yellow section, horizontal line, zero slope, zero velocity. But then at the end, steep slopes represent high speeds. So here we have an object that was moving at two different occasions, but the movement was not the same during those two different occasions. one time shallow slope, one time steep slope. Third example, we see here a line where this object starts off horizontally, or sorry, the graph of this object starts off horizontally, but then it takes a sharp downturn. And I'm going to use, and we'll go with peach for this one, right? So that sharp downturn right through here, okay? This is a constant slope. It is a straight line. However, it's different from the constant slopes that we've encountered previously in that it has a negative slope. Negative slope is okay. It's a downward sloping line. But in terms of our using the slope of this graph to tell us about the motion, right, that's still okay. We can have a negative velocity. Remember that velocity is a vector quantity. It indicates both the magnitude or the speed of a motion plus which direction it's going. So in this case here, if the object is moving in the negative direction or it has a negative slope, that just means the object is moving in the opposite direction or different from the way that it was originally moving. No problem, still a perfectly good example, just in moving in a different direction. So like I said, these are our initial applications of that idea that slope tells us the velocity of an object. And these are pretty simple graphs. We haven't encountered anything other than constant velocities. That's not the real world. So let's talk about those situations. So here we have a section where, or here we have two separate graphs where the the graphs of distance versus time or position versus time are not straight lines. They are curved. Curved lines have changing slopes. And if slopes change on a distance versus time graph, that means that the velocity changes. So, curved lines on position versus time graph represent changing velocities. In the first graph on the left, right, we start off and this graph has a pretty steep slope. And then a little bit later on, that slope decreases, and eventually that slope appears to be zero. It appears we've gone back to a horizontal line. If the slope starts steep, gets less, and ends up horizontal or zero slope, physically that would represent an object that is slowing down. It starts with a big slope, a big velocity, the velocity decreases, and then it becomes zero. But on the other hand, this picture over on the right, the slope starts off pretty shallow, gradually increases, and that would indicate an object that is getting faster or an object that is speeding up. So curved lines represent changing velocities, but how the line is curving tells us a little bit more about is it speeding up or is it slowing down. Now, that's qualitative analysis of these graphs, but we can get a little bit more quantitative. So let's take a look at this graph that we've already established is representing an object that is speeding up. Hopefully you remember from math class the idea of a tangent line. A lot of times we talk about it in terms of a circle, but more generally, a line that is tangent to any graph is a line that hits the graph in one spot and one spot only. So if we draw in this arrow very close to the bottom of the graph, we see that that line is sloping upward, so it has a positive velocity, but it's not a very steep line. Sorry, we're in between periods, so. A little bit farther on the graph, if we drew a second tangent line, we would see that the slope of that line has increased because, as we've already established, this object is getting faster. And then finally, when we get to the end, this is the steepest line of them all. Those slopes of those tangent lines can be used to calculate what we refer to as the instantaneous velocity. If you're not familiar with the term instantaneous, instantaneous refers to something that is occurring right now. So while this graph represents a velocity that is changing, we can figure out what the velocity of that object is at any specific moment by looking at the slope of that tangent line. On a position versus time graph, sorry, this should be x versus t, not t versus x, I apologize. On a position time graph that is curved, the slope of the tangent line tells the instantaneous velocity. Now in this class, we're not going to get real detailed in going into that idea or figuring out what the slopes technically are at those points in time. That's for a more advanced class. But know that if we did figure out the slope of this red line, or the slope of this red line, or the slope of this red line, that would give us the instantaneous velocity, or the velocity at time 1 second, because that's where that line is tangent to the graph, or 3 seconds, if that's where that one is tangent to the graph, or 4.75 seconds, if that's where that one is tangent to the graph. Those of you that are taking calculus, you'll learn that there is also another way to figure out the slope of these tangent lines, and that's using the derivative. I'm not going to get into that right now, but know that that's one application of your derivative, is finding the slope of these tangent lines, which can then give you an instantaneous velocity. One other thing we can talk about the graph is, or on this position versus time graph, is the difference between instantaneous and average velocity. I guess I should do this for you visual learners out there. Oh. Instantaneous versus average velocity. The red lines represent the velocity at one particular moment in time. The blue arrow represents the average velocity. Remember back from our discussion of a couple days ago that average velocity is related to the displacement over the time. Okay? S stands for displacement. Okay? Displacement is where we end versus where we started. So here, right, the total displacement here would be somewhere around 130 meters if that's where this ended up, right? 130 meters here. And then the time that it took was 5 seconds. Okay? So we could figure out the average velocity. Now, at the beginning, the instantaneous velocity is less than the average. The slope of this red line is smaller than the slope of this blue line. Somewhere in the middle, the slope of this red line and this blue line are exactly the same. But remember, the red line only has one spot where it's tangent to that graph. So there's only one point in time when that red line slope and the blue line slope are equal. And if you are keen on math and what averages mean, it's going to be right at 2.5 seconds. But then at the end, the red line has a steeper slope than the blue line. It's going faster than the average. Remember, average takes into account what was going on the whole time. So at the beginning, the velocity is less than average. At the end, the velocity is greater than the average. But the blue would represent the average velocity. Instead of speeding up like the green graph is doing, if we could take an object moving at a constant velocity, remember, straight lines like that blue one represent constant velocities. If we could go at the constant velocity that is equal to the slope of that blue graph, we would end up in exactly the same spot at exactly the same time as the object that was speeding up. Differences between instantaneous versus average. The second kind of motion graph that we want to look at is a velocity versus time graph. So, as you might be able to guess, right? Hold on one second. as you might be able to guess, a velocity versus time graph is a graph of the instantaneous velocity over a specified period of time. So now it's not telling us where something is, it tells us the speed or the velocity of that object at a specific time. If you recall from the previous video when we talked about our introduction to mechanics, position tells us where, velocity tells us what. So the previous graphs, the position graphs, tell us where something is. Velocity graphs tell us what it's doing. They can be a little bit tricky, but we'll talk about some of the things that we can use them for here in just a second. Much like the slope on a position versus time graph, the slope on a velocity versus time graph also can be used to infer some information about the motion. So here we've got a unit of, in this case, meters per second on the y-axis and a unit of seconds on the x-axis. Rise over run, right? Or delta y over delta x, meters per second over seconds. That's the unit for acceleration. Or, as IB would abbreviate it, meters over seconds squared, or meters times seconds to the -2 power. Right? This tells us how much is the velocity changing. So the slope of a velocity versus time graph tells us the acceleration of that object. If we look at these two graphs here, right, the blue graph on the left has a positive slope. Therefore, it has a positive acceleration. And if you were to describe what was going on, right, at 1 second, this object was going 4 meters per second. But at 2 seconds, now it's going 8 meters per second. And at 3 seconds, now it's going 12 meters per second. So when this object keeps going faster and faster and faster, positive acceleration implying that it is speeding up. But if we go to the graph over on the right, not to confuse you, right, but this is now a velocity or a speed graph, not the position graph that it was before. At the beginning, we have a horizontal line. In a position graph, a horizontal line means that an object is stationary. Its slope is 0, so its velocity is 0. That's on a position graph. But this isn't a position graph. It's a speed graph. So in this case, this horizontal line still has a slope of 0, but that means that its acceleration is 0. Remember, acceleration, by definition, is the change in the velocity. This velocity is not changing. It doesn't mean the object is stationary. It means that the object is not speeding up or slowing down. So, on a velocity graph, horizontal lines don't mean stationary. They mean constant velocity, a movement with a constant velocity. But then during the pink section, sorry, that was terrible highlighting. During the pink section, it's a straight line, so it has a slope, but it has a negative slope. And that means that it has a negative acceleration. If we were to do the same thing that we just did on the blue graph here, at 10 seconds, this object is going 5 meters per second. At 15 seconds, this object is only going 2.5 meters per second. And then at 20 seconds, this object has a speed of 0. It has come to a rest. So here, these velocity values keep getting smaller and smaller and smaller. Negative acceleration means that an object is slowing down. So again, we can infer something about the motion based on the shape of the graph, and then based on that telling us the acceleration. So we can tell if an object is speeding up or slowing down. And just like on the other graphs, let's say if we put a second time or velocity versus time graph, right, that looked something like this, both of those graphs would be objects that are speeding up, but one is speeding up faster than the other one. And same thing on this graph. If we put a second graph on here that looks something like this, that graph represents an object slowing down as well, but it's slowing down more quickly. It would be like a car slamming on its brakes or something like that. It has a negative acceleration, but a very fast negative acceleration, or a high negative acceleration, so its velocity changes very quickly. All right, one more thing that we can do on a velocity versus time graph that we can't do on a position versus time graph. We talked about how the slope tells us different things on both graphs, but there's one more thing that we can figure out from a velocity versus time graph, and that deals with the area under the curve. Now, there's no way this is intuitive. I wouldn't make you figure this out on your own, but let's say we filled in this space between the x-axis and the graph itself. That's the red triangle that I have highlighted here. And I can calculate the area of this red triangle. Hopefully you remember that we calculate the area of a triangle, base times height, divided by 2, or 1/2 base times height, however you want to say it. So here's the base of this triangle, and it's 4. But on this graph in particular, it's 4 seconds. So I'm going to plug that in here, okay? Times the height. On this graph, it's 16, but remember that 16 is a velocity. It's 16 meters per second. So I'm going to plug that in here. I realize that's not IB-ish notation, but it's going to work better for us here. That would be how we apply the formula for the area of a triangle to this specific time or speed versus velocity or speed versus time graph with the proper notation. So we would multiply 4 and 16 together, but when we multiply those numbers, we also have to multiply the units. There's a seconds on this unit. There's a meters per second on this unit. Seconds on the top, seconds on the bottom. Those two units cancel. And we would be left with 64 meters on the top, just plain old 2 on the bottom, no unit involved with that number. And so that then simplifies to 32 meters. Notice, it's a meters number. It's a distance. This graph, we said, because it's a speed graph or a velocity graph, right, tells us what an object is doing, not necessarily where it is. But we can use the information on this graph to figure out how far did that, how far did that object go in the time that it was speeding up. So the slope of a speed graph tells us the acceleration, but the area under the curve, this red triangle, represents the displacement of that object during that time. So to summarize, right, the area under a velocity versus time graph, we should go v versus t here, sorry about that, equals the displacement. Again, those of you taking calculus, there's another way that we can do this for regular shapes like triangles, but also for irregular shapes like curves and parabolas and things like that. In calculus class, we use the integral, which you'll get to eventually if you're taking calculus. We can apply this idea to any kind of velocity graph. So here's this graph that we were looking at before. We said that during this section right here, zero slope means zero acceleration. It's not speeding up or slowing down. It's going the same speed. But then, from this point on, negative acceleration, so that object is decreasing in speed. But it's still moving, so it's still going forward while it's decreasing in speed. Here, we could make the area under this curve out of two regular shapes, a rectangle and a triangle. So if we wanted to calculate the total displacement, we'd have to add the areas of these two regular shapes, right? So here, this is 5 meters per second times 10 seconds. This is just a rectangle, so base times height. And that means here, before the object even starts slowing down, it has already traveled 50 meters. But then from this point here to the time when it stops, we have a triangular shape, so base times height divided by 2. The base of this triangle, 20 seconds, times the height of this triangle, which is 5 meters per second. Divide that by 2. You do a little bit of math, right? 20 times 5, hopefully we know. Oh, wait, my bad. This is not 20 seconds, even though it ends at 20 over here. It didn't start slowing down, right, until the 10-second mark, so this is only a time of 10 seconds. 10 times 5 is 50 divided by 2. That's 25. So this object, during the entire time of this graph, would travel 75 meters as we add together the area of both of those red shapes. Okay? One last thing on velocity graphs. More often than not, you're going to see velocity graphs that show up on the positive side of the x-axis and on the negative side of the x-axis. That's okay. Remember, velocity is a vector quantity. So it has to tell us two things. It has to tell us the magnitude, or how fast something is going, but it also has to tell us the direction and which way that it's going. And remember, in one dimension, so we're still in one dimension here, in one dimension, we specify direction through the positive sign and the negative sign. Is it going this way or is it going that way? Because remember, in one dimension, there's only two choices. So more often than not, you're probably going to see graphs where an object starts on one side of the x-axis but ends up on the other side of the x-axis. As the sign flips from positive to negative, that means that an object is changing direction. Interesting point here, right? During that little section right there, we have a horizontal graph, meaning that on this velocity graph, there's no acceleration. But in this spot in particular, because that horizontal section is on the x-axis, the x-axis represents zero velocity. So this graph at this, or the object at this point in time, has no acceleration. It's not changing what it's doing, but specifically, it's not changing from 0. So there are times when horizontal lines on velocity graphs can be an object at rest, but they have to specifically be on the x-axis. All right. I hope that helps. Tomorrow in class, we'll start applying these ideas, looking at some examples. There is some homework, so take a look at it there, and we will talk tomorrow.